Hello my shimmering stars, today I Shaurya Grover welcome you all to this amazing platform of PW English. Students, I welcome you all to your Nexus Batch and today we are going to start with your next topic of P block elements chapter, that is going to be group number 14. So I welcome you all to your lecture number 3rd with regard to the chapter P block elements, and I hope so students you have revised the previous topic and you are very well aware of that. So let's proceed with today's segment, and I hope so you have done the previous questions also. So ma'am, how are we going to proceed today? How are we going to proceed further in this particular class? Let me tell you, as students we were discussing for the boron family. You very well remember that we have done the physical properties, we have done the chemical properties, and then we have done the compounds related to them. So in the same manner, we are going to proceed with the carbon family. We shall be doing the physical properties, then we shall be doing the chemical properties, and then the compounds related to them. So students, at the end of the lectures, that means the last lecture that we are going to have tomorrow, we'll be completing all the question segments in detail with regard to the groups that we have studied in your P block element chapter. See, 13th and 14th group is in class 11th and rest in class 12th. So basically all the question segments will be held in the next lecture. In today's session, we'll be understanding about the theoretical concept about your group number 14th elements. So let's start this with a wonderful and a beautiful smile. Okay. So now ma'am, how are we going to proceed? What are the topics we are going to cover in today's segment? So basically students, we are going to start with the introduction part. Okay, that what exactly is group number 14th? What it is referred to as? What are the elements present over here? And why are the elements present under group number 14th only? Why are those elements not placed under group number 13th or 15th or under S block? What is the reason behind it? So we are going to understand about that as well. Moving forward students, we shall be understanding about the electronic configuration and the atomic radii part. Okay. Now in electronic configuration, then we will be doing so. We will be again learning them with the help of magic numbers. As we have done with regard to the boron family, if you remember, we have given a trick for the magic numbers, that was 8, 18, 18, 32. Very simple technique. In the same way, we will be doing this part as well. Moving on to the next, we will be doing the atomic radii. Now we will be seeing the trends of covalent radii when we are moving from top to bottom. What is the effect on covalent radii? We will be doing that. Coming forward, students will be understanding about physical properties and the chemical properties. Clear? Okay. So let's start this very first part, that is basically going to be the introduction segment. So see students, let me tell you what are the members that are present in the carbon family. So that is carbon, silicon, germanium, tin and basically lead. These are the members that are present under carbon family. So C represents your carbon, Si represents your silicon, Ge represents your germanium, okay, Sn represents your tin and Pb represents your lead. Yes everyone. So first of all, let me show you all of these in the periodic table that we study. This is the periodic table that everyone has at home, right? Now let me widen up. See students, over here, if I am telling you where are group number, 13, 14, 15, 16, 17 and 18 elements. So they lie at the right hand side position of the periodic table, as you can clearly observe. That basically if I talk about the complete periodic table, I have these as my S block elements, then these are your D block elements and here is basically your P block elements. These are your F block elements, right everyone? So basically if I'll talk about the P block elements that we have started, we have already covered, boron, we have covered aluminium, gallium, indium and thallium. So basically these are group number 13th elements that we have done. But today we'll be moving on to carbon, silicon, germanium, tin and lead. Yes everyone? We'll be doing this part. See students, all of these elements, carbon, silicon, germanium, tin and lead, these lie under which group ma'am? Under 14th group. Okay ma'am. Okay. What else ma'am? What else ma'am? See, these basically are your group number 14th elements. Okay. But they are also referred to as carbon family. They are also referred to as ma'am carbon family. Carbon family. So do remember this part, that they are also referred to as carbon family, though there are group number 14 elements. Why it is referred to as carbon family, ma'am? Because the initial element of this particular, if I'll talk about the group is carbon. That's why. Now coming to the next part, students, that what are the occurrences? Where are they, are seen, they are observed. So if I'll talk about the very first, that is carbon, it is basically present in two forms. Okay. One is the elemental form. One is the elemental form, and another one is the combined form. Okay. The very first form is elemental form, the second form is combined form. Now, what is an elemental form and what is a combined form, ma'am? Elemental form is that form when basically the carbon atom is present either in the graphite form, in the diamond form. That means it is not combining with any other element, okay? If I'll talk about the combined form, in combined form, it is either creating a molecule, it is either creating a compound. That is what is referred to as a combined form. So, elemental form is a state when it is present in the form of elements, that means carbon, the graphite form, the diamond form, but in the combined state, it is present as a compound or as a molecule. For example, it is existing in the hydrocarbons. For example, it is existing, as a carbonates. For example, it is existing as CO2. So, that is what is a combined form. Point clear? Okay, ma'am. If I'll talk about, silicon over here, silicon exists in the form of silica, in the form of silicates. Yes, everyone. So, this basically exists in silica or in the form of silicates. If I'll talk about germanium, students, so germanium is basically used, as a semiconductor. It is used generally as a semiconductor, students, right? Also, students, if I'll talk about tin and lead over here, you will be observing that their ores are being observed. They are present in the ore form. Moreover, okay, I'll be talking that which ore form is observed in both of the cases, like tin will exist in the oxide form and PB will exist as a PBS, the galena form, right? So, let's talk about their discussion, students. So, if I'll talk about their occurrences over here, I have major key points. But before moving on to the major key points, before discussing the very first major key point, let me tell you one more thing about the carbon. See, carbon, students, can exist in three isotopic forms. Three isotopic forms. Now, what are the three isotopic forms of carbon if I'll talk about? So, the very first is carbon 12, then is carbon 13th, then is carbon 14th. So, these three are the isotopic forms of carbon in which we shall observe that their atomic number is same. Now, if someone don't know what is an isotopic form, what is an isotope? Let's discuss about that first. What is an isotope? Students, isotope is something when elements have same atomic number, but different mass number. Okay, so if I'll represent a certain element X and I will be writing the atomic number at the base and mass number at the top. So here Z represents your atomic number, Z represents your atomic number, A represents your mass number. Very simple part, very easy part, right? Now, if I'll talk about the three isotopic forms that I have written over here, you can clearly tell me that, ma'am, in this 666 represents your atomic number, which is same in all of these three, while 12, 13th and 14th are your mass number, which is different in all of these, right? Here it is 12, here it is 13, here it is 14, so which are basically different over here. Yes, everyone. So, this is what is mass number represented. Now, what is mass number? Mass number is atomic mass, or I would say the sum of neutrons and the protons. Clear with this part also? So, this was the general part that we should know. Now, coming to, the isotopic forms also, let me tell you that carbon in 12th and 13th isotopic form are stable isotopes. They are basically stable isotopes, right? So, let's write this down. Everyone, just take a minute, write each and everything that I have written over here, so that now I can move on to the next part of mine. Clear, everyone? Take a minute, write it down. See, students, Now let's read all the characteristics that is written over here. Naturally occurring carbon contains two isotopes, that is carbon 12 and 13. Now they are naturally occurring isotopic forms. Now see, in addition to these, third isotope, that is C14 I am talking about, is also present, but it is a radioactive isotope and is used for the radiocarbon dating process. Now what is the radiocarbon dating process? Which basically determines the age. Students, clear? Now, which is going to determine the age, that is basically the radiocarbon dating process. And over here, carbon 14 basically helps to, is basically used over that in that particular process. It is a radioactive isotope. So, this initial point which I have written over here is very, very important. You need to put a star mark over here. Clear everyone? Okay. Now comes the silicon part. Silicon is a very important component of ceramics, glass and the cement. Clear? Moreover, if I'll talk about germanium, germanium exists only in traces. Moreover, it is used as a semiconductor. Coming to the next is tin. Tin, if I'll talk about, mainly occurs as a casterite form. Okay, that is SnO2. I told you, no, basically it is a kind of an oxide. So that is basically SnO2, the cassiterite form. Now this question is also again and again asked. Okay, and if I'll talk about lead exists as galena. I already told you, no, galena, that is PbS. So this is also an important part. So these are basically the carbon family compounds and their existence. How do they exist in nature? What is their existence? Clear everyone? That's great. Okay, ma'am. Now what next, ma'am? Shall we start with the electronic configuration? But before the electronic configuration, let's talk about which is metal, which is a non-metal, which is metalloid. So students, if I'll write carbon family, carbon, silicon, germanium, tin and lead over here, let me tell you very clearly that if I'll talk about, carbon and silicon, they both are non-metals. Carbon and silicon, they both are non-metals. If I'll talk about germanium, students, it is a metalloid. If I'll talk about germanium, it is a metalloid. Then about tin and lead, they both are metals. They both are what? Metals. Right. Let me tell you again, what are non-metals, what is metalloid and metals over here, you very well know. Right. Now, in all of these three students, in all of these metals, non-metals and metalloids, if I'll talk about the trend from top to bottom, you can clearly observe and tell me that ma'am, metallic character is going to increase, non-metallic character is going to decrease, right? So, if I'll talk about metallic character over here, if I'll talk about the metallic character over here, so metallic character, students, increases. It basically increases down the group. Very easy part, right? What about non-metallic character, ma'am? Non-metallic character. Non-metallic character. Now see, it is basically decreasing. Non-metallic character is decreasing down the group, metallic character is increasing down the group. Very simple part, very easy part, you can clearly observe it. Now students, let's proceed with the next part, that is electronic configuration. But before that, let me tell you, they all are solids. The carbon family, they all are solids. They all are solids. Clear everyone? Okay ma'am, okay ma'am. Just take a minute students, write all of the things that I've written over here and then I shall proceed towards the next part. Clear? Okay ma'am. Now comes electronic configuration. If I'll talk about the electronic configuration, let's first of all write the elements, that is carbon, silicon, germanium, tin and lead. Now see, in this particular part students, first of all we should know the atomic numbers of each and every one of them. See, if you know the initial element's atomic number, that is carbon is 6, you can clearly tell the atomic numbers of other elements. How ma'am? What is the magic rule? The magic numbers. The magic number is 8, 18, 18 and 32. This is basically the magic number that we are going to use. That means 6 plus 8 comes out to be what ma'am? 6 plus 8 comes out to be 14. Now 14 plus 18 comes out to be what, ma'am? 14 plus 18 is 32. Now 32 plus 18 comes out to be what, ma'am? It is basically 50. Now 50 plus 32 is basically 82. Clear, everyone? So these are the atomic numbers that I have written. It's very simple. You have to just add 8, then 18, then 18 and then 32. You just have to add these numbers. See, 6 plus 8 is 14, 14 plus 18 is 32, 32 plus 18 is 50, 50 plus 32 is 82. So basically these are the atomic numbers that we have determined just with the help of initial elements atomic number. So if you remember that, everything will be more and more and easily clear to you all. Right, everyone? Okay, ma'am. Now let's talk about, the general electronic configuration. So if you remember, my dear students, I've already told you that if I'm writing, here is my group number 13th, here is my group number 14th, here is my group number 15th, group number 16th, group number 17th, group number 18. Basically, these all are your P block elements. These all are your P block elements, right? And if I'll tell you the general electronic configuration trend, here the general electronic configuration is NS2NP1. In this part, it is NS2NP2, for which group number 14, NS2NP2. If I'll talk about group number 15, it is NS2NP3. If I'll talk about group number 16, it is NS2NP4. For group number 17, it is NS2NP5. And for group number 18, it is NS2NP6. Yes, remember? Okay. N here represents your period number of the shell number, outermost shell I'm talking about. The period number or the outermost shell, and these configurations that I have written over here. These configurations I have written is outermost shell, this is general, outermost shell, general electronic configuration. Outermost shell, general electronic configuration part. I hope so, students, this is clear to each and every one of you. Yes, everyone. So this is basically outermost shell general electronic configuration that I am talking over here. This is NS2NP1, NS2NP2, NS2NP3, NS2NP4, NS2NP5, and then comes NS2NP6. Now, why are they referred to as P block elements? We have already covered about this part because, ma'am, here the last electron enters into the P subshell. See. And we very well know that P, basically there are 3 orbitals of P. If I'll talk about the P orbitals, there are 3 P orbitals, that is basically your Px, Py and Pz respectively, and each orbital contain maximum 2 electrons. So it's, for example, 1, 2, 3, 4, 5 and 6. That means total 6 electrons can be only present in the P orbitals. That means only 6 electrons can be present. So if I'll talk about the very first case of group number 13, there is 1 electron that is present in the outermost shell of the P orbital. In the second one, group 14, 2 electrons are present in the outermost shell of P orbital. In 15 it is 3, in 16 it is 4, in 17 it is 5, in 18 it is 6. So if I'll talk about the general electronic configuration for group number 14 students, that comes out to be what, ma'am? NS2NP2, where N represents your period number. So this is the general electronic configuration, right? Now let's write the general electronic configuration. See, let me tell you, for carbon, N value is going to be 2. Okay. For silicon, N value will be 3. For germanium, N value will be 4. For tin, N value will be 5. For lead, N value will be 6. Yes, everyone. These are the period number that I have written over here. And if I'll talk about the very first part, its outermost shell configuration is going to be 2s2, 2p2. For silicon, it is going to be 3s2, 3p2. For germanium, it is 4s2 4p2. 14 it is 5s2 5p2, and for lead it is 6s2 6p2. Yes. Now let us confirm, let us do the general, let us write the complete electronic configurations for the initial two elements so that you can get an idea. See, if I'll talk about carbon, let's take an example of carbon only. Carbon has an atomic number 6. So we can write it as 1s2, 2s2, then 2p2. See, always remember, S can hold maximum 2 electrons, no? So 1s2, 2 electrons done, then 2s2, 2 electrons done. Just count the number of electrons. 2 plus 2 is 4, 4 plus 2 is 6. So the last electron enters into the second, period, and into the p there are 2 electrons. Last electron enters into the p subshell, there are 2. So it is ns2 np2. This is ns2 np2. See, this represents the first period, this represents the second period. So second period contains how many electrons? 2 of s and 2 of p, that is 4 electrons. Coming to the silicon part. Silicon has an atomic number, what ma'am? 14. So it is going to be 1s2, 2s2, now see 2p6, why? Because p can hold 6 of maximum electrons. So 2 plus 2 is 4, 4 plus 6 comes out to be what ma'am? 4 plus 6 comes out to be 10. After 10 students we have what? 3s2, 12, now 2 is left, so it is 3p2, 14. Clear everyone? So this is basically the first shell, the second shell, and this is the third shell, the outermost shell. So the outermost shell configuration is ns2 np2. Clear with this part everyone? Clear with this part? Now, telling more important things over here. Carbon has a covalency of 4. Carbon has a covalency of 4. But if I'll talk about the other elements, that is silicon, germanium, tin and lead, they can basically have, covalency. They can exceed the octet rule. Exceed or extend basically the octet rule, and have more than 4 covalency. So they can have more than 4 covalency, but carbon has a covalency of 4. Now what is a covalency? What is a covalency, ma'am? Covalency is combining capacity. Covalency is combining capacity of any element. Combining capacity of any element is referred to as its covalency. Clear everyone this part? I want you people to write each and everything that I have written on the board so that I can move on to the next slide. I hope so the electronic configuration portion is clear to each and every one of you. Though with this part I have explained you each and everything that is about the general electronic configuration that you are going to remember for this class, also for the next class also, that means for class 12 standard as well. Moreover students, I had told you about the covalency part that you should know, and sometimes students just skip it out. See, now why I have written this over here, I have highlighted with the important key points. Why? Because in question paper they are going to give you such compounds. They will say that which of the following has a covalency of 4, only 4, then that is only carbon, because the other basically can exceed their covalency. Now covalency is combining capacity, that it can create 4 bonds over there, carbon if I'll talk about. Yeah. Okay everyone, now let us start with the physical and the chemical properties, and we'll be starting with the atomic radii portion. So before that I want you people to write it down, to note each and every concept over here. Clear? Yes ma'am. So now let's start with the very first property of ours, that is atomic radii. And in atomic radius also, I will be talking about covalent radii. Why I am saying that? See students, before understanding the covalent radii, we very well know where I am talking about covalent radii, there shall be a covalent bond created. Now see about carbon. Carbon basically is atomic number 6. So it is 1s2, 2s2, 2p2. Yeah, so if I am going to write, if I am going to fill the electrons, it is going to be like this, no? Now in the excited state, what happens students? In the excited state, this electron jumps over here and we get like this state. And so only 4 bonds can be created. 4 bonds can be created over here. It's very simple. Let me tell you. Carbon basically, has a covalency of 4. It has how many valence electron in its outermost shell? Carbon basically has 4, valence electrons in the outermost shell. So now if it has 4 electrons in the outermost shell, what it is going to do? It is either going to, lose all the electrons, or it is either going to gain all the electrons. What it is going to do? It is going to share the electrons. See, when there is a sharing of electrons, that creates a covalent bond. Always remember, when there is a sharing of electrons, the sharing of electrons, that is a covalent bond created. In covalent bond, there is only sharing. There is no loss of electron, no gain of electron. It's only and only sharing of electrons. So here you can clearly see that there is no loss of electron, no loss of electron done, or no gain of electron done. It's just sharing of electrons. Sharing of electron takes place. That creates students a covalent bond. That creates which kind of a bond, ma'am? That creates a covalent bond. Also students, if there is no loss of electron, no gain of electron, so it is neither Lewis acid nor Lewis base, because it is neither gaining electrons nor it is losing electrons. So it is neither Lewis acid nor Lewis base. Whom I am talking about? I am talking about carbon. I am talking about carbon. So just don't get confused with this part. Just don't get confused with this part. This is extra knowledge that I am giving, that you can read from the NCERT also. So carbon basically can just do sharing of electrons. Carbon just can do sharing of electrons, that is creating a covalent bond. And hence the radii that I am talking over here is covalent radius. How does it looks like? For example, it is the radius of the first one and it is the radius of the second one. So this is basically the sharing of some electrons, okay. So this is basically a structure of the covalent radii. This R here represents covalent radii, okay, when there is a sharing of electrons. This is basically, students, over here, this area is basically the sharing of electrons. This is the overlapping region. Here overlapping is seen, where electrons are being shared. So this creates which kind of a bond, ma'am? This creates a covalent bond. And which radius is observed over here? That is a covalent radius. Okay, this is what is a covalent radius. Clear everyone with this part? Okay, that's great. Now let's discuss about the trends with regard to the atomic radii. That is the covalent radii. See, if I'll talk about the trends with regard to the covalent radii, students, see, we have carbon, silicon, germanium, tin and lead. Let me tell you what happens from top to bottom. What happens from top to bottom, ma'am? From top to bottom, number of shells will increase. So the covalent radii will also increase. Let me explain how. See, we very well know the general electronic configuration for carbon is 2s2 2p2. For silicon is 3s2 3p2. For germanium is 4s2 4p2. For tin is 5s2 5p2. And for lead is 6s2 6p2. Yes, everyone. So if I'll draw carbon, carbon basically, if I write the initial configurations, you very well know. This is second shell, no? Outermost shell. These are basically your outermost shell, no? These are basically your outermost shell, no? So if I'll start with the very first that we have, this one. So this is basically the nucleus. This is your first shell. This is your second shell. Second shell contains 4 electrons. Let's talk about silicon. This is your nucleus, first shell, second shell, and then comes the third shell. Now third shell contains how many electrons, ma'am? 4 electrons. Let's talk about germanium. This is first shell, second shell, third shell, and then the fourth shell. Yeah, so it contains again 4 electrons in the outermost shell. Let's talk about tin over here. Nucleus, first shell, second shell, third shell, fourth shell, and then the fifth shell over here. Yeah. So now the last one is basically the lead. If this is nucleus, first shell, second shell, third shell, fourth shell, fifth shell, sixth shell. So what you are observing over here, students, what you are observing from top to bottom, if you are going, the distance from the center to the outermost shell electron is going to increase. What is a radii? What is a radii? Radii is basically distance from the center to the outermost shell electron. This is what is the radii now. So you can clearly see that distance from the nucleus to the outermost electron, distance from the nucleus to the outermost electron, distance like this. So what you are observing, the distance basically is increasing. That means on increasing the number of shells, covalent radii is going to increase. So this is the very simple trend, very basic trend with regard to atomic radii. Just take a moment, students, write it down. So that now we can see the next part. We can start with the next part. Okay. Now this was about from top to bottom. Yeah. Let's talk along a period. Let's talk along a period. That means if I'll talk about group number 13th and group number 14th. Because we are comparing both of these groups. So let me tell you, students, when you're moving from left direction towards the right direction, from left direction towards the right direction, what you're going to observe that, ma'am, nuclear charge will increase. Okay, if nuclear charge increases, size is going to decrease. Okay, that means group number 13th has more, radii than group number 14th. This is a longer period. Group number 13th has more radii than group number 14th. Clear, everyone? Nuclear charge from left direction to the right direction is going to increase, which is going to decrease your size. Now, what is the nuclear charge? Okay, this is basically the force exerted by nucleus on outermost shell electron. On outermost shell electron. This is what is a nuclear charge, everyone. This is what is a nuclear charge, everyone. Clear with this part? Clear with this part? Just take a moment, write it down so that I can start with the next trend now. Okay. Now, students, I'm going to start with the next trend, that is ionization enthalpy. See, what is an ionization enthalpy or an ionization energy? This is basically the minimum amount of energy that is required to remove an electron from the outermost shell of an isolated gaseous atom, This is what is an ionization enthalpy or an ionization energy, that minimum amount of energy that you're giving so that the outermost electron can be removed out. Okay. Now, students, let's talk about, the trend in a period. First of all, a longer period. See, if I'll talk about a longer period, now I'm talking about group number 13th and group number 14th. See, let me tell you first of all the various factors on which ionization enthalpy is going to depend upon. Yeah. So, see, the very first factor, students, is going to be size. Ionization enthalpy is inversely proportional to size. More the size, less will be ionization energy or ionization enthalpy. Less the size, more the ionization enthalpy or the ionization energy. Let's take a general example. See, students, for example, I am having a smaller, atom. Now, if I am having a smaller atom, that means the force of attraction of the nucleus on the outermost electron is very, very strong. And if it is very strong, you have to give it a lot of energy so that the electron can be removed out. Clear? Now, let's take a case when we have a larger atom. If you are giving a very less amount of energy, then also it can be easily removed electron. Why? Because the distance now from the center to the outermost shell electron has been increased. And if the distance has been increased, force of attraction has been decreased. Clear with this part? Yeah. So, basically that means more the size, less the ionization energy, or less amount of energy you will be giving, but lesser the size, more the ionization enthalpy will be given, more the energy will be given. Why? Because there is a stronger force of attraction. Now, let's talk about the second factor, that is electronic configuration. See, students, if I'll talk about electronic configuration, as you very well know, if for example, we have to remove one electron from the outermost shell. Yeah. So, if I'll take a case when there is a fully filled electronic configuration, let's consider when we have a fully filled electronic configuration. Now, in that case, students, what you have to do? You will be providing a lot of energy. Why? Because it is already stable. See, what is the stability order if I'll talk about the fully filled, the half filled, or the something which is partially filled? Fully filled will be more stable, then the half filled, and then the partially filled. Yeah. So, in fully filled electronic configuration, which is completely filled, which has all the electrons completely, you have to give a lot of energy to remove the electron from the outermost shell, and then comes the partially, and then then comes the half, then comes the partially. Why is it so? Because they're already stable. You are affecting their stability. Yeah. So, basically, fully filled will have a higher stability. That's why you have to give a higher amount of ionization enthalpy over here. Then comes your half filled, and at last is your partially filled. Clear with this part, students? Yes. Okay, coming back over here, if I'll talk in group number 13th and 14th, see what is going to happen over here. As you're moving from left to right direction, nuclear charge will increase. Size will decrease. If nuclear charge will increase, size will decrease. I already told you that ionization enthalpy or ionization energy is inversely proportional to size. So, right. So, ionization enthalpy will increase. And one more factor you can clearly write, which you can clearly observe over here, that nuclear charge, ionization enthalpy or energy is directly proportional to nuclear charge. Now, only in the previous slide I told you what is a nuclear charge. Nuclear charge is basically the force exhibited by the nucleus on the outermost shell electron, right? If that force is increasing, that means force of attraction is increasing. If force of attraction is increasing, electron from the outermost shell will come inside, and if it comes inside, you have to give a lot of energy to remove that electron. Getting my point? So, basically this is the trend that you need to remember over here for the period, along the period. Yeah. Now, let's talk about a longer group. Now, students, when I'm talking a longer group, it is carbon, silicon, germanium, then we have tin, and then we have lead. See, from top to bottom, it's very simple, ma'am, that number of shells are increasing. What is happening? Ma'am, number of shells are increasing. That means, ma'am, radii or the size is also increasing. Radii or the size is also increasing. Ma'am, if it is increasing, ionization energy will decrease. So, students, if it will decrease, what is going to be the trend? Carbon will have highest like this, but over here the trends change. Here there is an exception, here there is an exception. Why is it so? This is due to lanthanoid contraction. Now, what is a lanthanoid contraction? See, basically f orbital starts to get filled up. And when we talk about f orbital basically has a poor shielding effect. it basically has a poor shielding effect. And now when something has a poor shielding effect, that means the inner electrons cannot protect with the nucleus from the outermost electron. Outermost electron will come inside. If it will come inside, what will happen? What happened to size? Size will decrease. Yeah. So ionization enthalpy will increase. That means in the case of lead and tin, lead will have more ionization enthalpy than the tin. Clear with this part? Everyone just take a moment and write it down. This was about ionization enthalpy trend. This was about ionization enthalpy trend. Now we'll be talking about the electronegativity trend. Just take a moment, write this down. Then we shall be discussing about the electronegativity trend. Right, everyone? Okay, ma'am. Let's talk about electronegativity now. What is an electronegativity? Electronegativity is the tendency to attract shared pair of electron towards itself. What is an electronegativity? It is the tendency to attract shared pair of electron towards itself. Okay, the tendency to attract shared pair of electrons is electronegativity. For example, if I am electronegative, I am attracting electron towards me, so I will gather with charge a negative charge. Okay, and if I am releasing electrons, I have a tendency to do that. That means I am basically what I mean, I am electropositive in nature. So now talking about electronegativity, see students, carbon, silicon, germanium, tin and lead. Now see, let me tell you, electronegativity trend should be like this, that number of shells basically, if they are increasing, size will increase, electronegativity will decrease. This should be the trend. But see, it will decrease, but we observe that only carbon basically have the highest electronegativity, rest almost have the same electronegativity. Clear with this part? Just write down, students, this is again an exception, yet an important one, and you should remember this part as well. Clear with this one now, everyone? Yes, everybody? Okay. Now let's proceed towards the next one, that is basically the oxidation state. That is, what is an oxidation state we are talking about. Students, oxidation state or oxidation number is one of the same things. It is basically the formal charge in any element. The formal charge in any element is basically the oxidation state or the oxidation number. Now let me talk about the carbon family. It's carbon, silicon, germanium, tin and lead. Now in C, this part, let me tell you, the common oxidation state for the carbon family is common oxidation state for the carbon family is +4 and +2. +4 and +2. Okay, now let me tell you thing over here. The higher oxidation state value, or I would say the higher oxidation state stability, is going to decrease down the group, and lower oxidation state stability will increase down the group. Okay. One more thing, students, let me tell you, carbon can exhibit -4 oxidation state also. It can exhibit -4 oxidation state also. Clear with this part? Now see, why this happens, that lower oxidation state stability increases and the higher oxidation state decreases? Due to the inert pair effect of the lower ones. So if I'll talk about over here, see, carbon in +4, carbon in +2. Now see, let's talk about the one from which question is asked. See, till here, students, till here, what happens? +4 is more stable till here. But in case of PB, what happens? For example, Sn is in +4, Sn is in +2. So it is more stable. But over here, PB +4 and PB +2. PB +2 will be more stable. Why is it so? Why is it so, ma'am? Due to inert pair effect. Now, what is an inert pair effect if you want to write down? This is reluctance of s orbital to participate in bonding. Reluctance of s orbital to participate in bonding, that they are no longer participating in bonding, and hence only the oxidation state will come out to be 2 for that case. Now CV, why? Because it is NH2 NP2, right? If s orbital are not participating in bonding, there will be only 2 electrons, no, and hence the oxidation state comes out to be clear. Clear? That is 2. Clear everyone? Just write it down, students. Now I am giving you certain question as a homework which you should solve it and try to solve it out, okay? And it's very easy, students, if you'll do that, okay? So the question over here as a homework is the stability of tetrahalides of silicon, germanium, tin and lead increases in order of first option is Pb plus 4, Sn plus 4, Ge plus 4 and Si plus 4. Second option is Si plus 4, Ge plus 4, Sn plus 4, Pb plus 4. Third option is Pb plus 4, Ge plus 4, Si plus 4, Sn plus 4. While fourth option is Sn plus 4, Ge plus 4, Pb plus 4 and Si plus 4. Clear? This is your first homework question. I hope so you all have written this. Clear? I guess you all have written this. Now, one more question as a homework, students. The bond dissociation energy of bond decreases in order of first option is SN, then GE, then SI, and at last is carbon. Second is carbon, then SI, then GE, then SN. Third is carbon, fourth also I am writing along with carbon. Here is GE, here is SI, here is okay, students. So these are two questions over here as your homework, which you have to try to solve it out. It's very easy, very simple. Just do it, you will get your answer. Right, everyone? Now, the next chemical properties that we'll be talking about and the compounds related topic we'll be doing in the next class. And we'll be winding up the P block chapter in the next class. The next class duration will be quite long, students, where we'll be completing with the question segments also with regard to 13th, with regard to 14th, and with regard to the chemical properties and the compounds of them. Yes, everyone. I hope so today's session was clear, and when you are doing, the group number 13th, 14th part, you come across the thing that they're so similar to each other. Yeah. So if you understand one of the properties, the periodic properties like atomic radii, ionic radii, covalent radii, ionization enthalpy, electronegativity, electron affinity, then you will be able to, tell all the physical properties of each one of them. And even if I talk about oxidation states also, they're so similar with each other that in the previous case, we saw that, the oxidation state value came out to be what? It was either +3 or +1. Over here, it is either +4 or +2. So, it is very easy to remember each and everything over here. But yes, before, applying them into questions, you should revise it first. So your today's homework is, students, to solve the question that I've given over here as a homework. Moreover, read NCERT, because see, we are not doing a, I would say, a lot of concepts altogether. We are doing very small concepts and covering each and every part in detail. And I'm not giving a lot of homework also. Yeah. So you can clearly read NCERT. You have a lot of time now, but in future you won't be having this time, right? So utilize it as much as possible, my dear students. Now, students, I shall be meeting you in the next class with the next topic of yours. Till then, keep smiling, keep learning. Thank you so much and take care of yourself. Thank you.